Hello everyone. Today we are going to look at section 3.6 using perpendicular and parallel lines. Our goal is to prove lines are parallel and perpendicular. So we're actually going to use a lot of the things that we've already learned in chapter 3 and add just a few new things on. Here's your first postulate, postulate 10, parallel postulate. In words, if there is a line and a point not on the line, then there is exactly one line through the point that is parallel to the given line. I know that sounds like a lot. So look for a few things. If there is a point not on the line, okay, then there is exactly one line through the point that makes it parallel to the given line. Those are just some keys. So here's some symbols down here. It's a lot of words, but the book gave this as the symbols. If P is not on L, so the symbols means that it matches up to this diagram right here. If P is not on L, so here's P, here's your line L, right here. So if P is not sitting on that line, then there exists one line, M, through P such that M is parallel to L. So we can draw one line through this point P. We're going to call it M right there. And there's only one line you can make that is actually going to turn out to be parallel to this one. Okay? Hopefully that makes a little bit of sense. Postulate 11, perpendicular postulate. So this is basically the same thing, except instead of having a line parallel to L, we have a line perpendicular. So in words, if there is a line and a point not on the line, so the same thing, a point not on the line, then there is exactly one line through the point that is perpendicular to the given line. Okay. So here's our symbols that speak directly about this diagram. So if P is not on L, so here's P, here's your line L, hopefully you can tell P is not on that line, then there exists a line M through P such that L is perpendicular to M. So there's only one way that we can draw this line through P so that we get a right angle. Because remember, all perpendicular lines have to form a right angle. Perpendicular lines, I'm just adding this in, form a right angle. That is definitely a basic level, not a basic knowledge level question or a basic knowledge level item, that perpendicular lines form right angles. Theorem 3.11. If two lines are parallel to the same line, then they are parallel to each other. Okay, so right here again, the symbols deal directly with this diagram right here. So you have two lines that are parallel. So these two lines are parallel, Q and R. You can tell because they have those thick black arrows right there. And then you also have R and S parallel. Okay, so think about that for a second. If S is parallel to R and R is parallel to Q, doesn't it make sense that Q has to be parallel to S, the beginning and the end? This is very similar to the transitive property. Number T for 3. So in symbols, if Q is parallel to R and R is parallel to S, then Q is parallel to S. So you can see that R right there in the middle, take out the middleman with the transitive property, and this really is the same thing. Okay. Theorem 3.12. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Okay, so here's your symbols again, having to do directly with this diagram to the right. So if M is perpendicular to P and N is perpendicular to P, then M is parallel to N. So think about this for just a second. Here's your P. We've got that labeled. So M right here makes a 90-degree angle with that. N right here also makes a 90-degree angle with that. Okay, so if these two both form right angles with P, then M and N have to be parallel. You can also go back and use your corresponding angles postulate to help you with that. If you remember from last time, we said that if corresponding angles are congruent, then, or therefore, we have parallel lines. And that's really the same thing that's happening here. We have this right angle marked, and then we have, so we have this right angle marked, and then we have this right angle marked, and those are corresponding angles. So if corresponding angles are congruent, then we have parallel lines, okay? But it's this postulate, or this theorem right here, theorem 3.2, that says, hey, they're not just corresponding, they're perpendicular. So if you get right angles, then you also have parallel lines. So here's an example. Use properties of parallel lines. Ladders were used to move from level to level of cliff dwellings. Each rung on the ladder is parallel to the rung immediately below it. Explain why. L would be parallel to P. So we want to know why this L right here is going to be parallel to this P right here. Okay? We'll use the information you were told at the very beginning of this. Ladders were used to move from level to level. Each rung of the ladder is parallel to the rung immediately below it. So that means that L is parallel to M. And then, I'm going to color code these, M is parallel to N. And then also, N is parallel to P. Does it make sense that they would have to be, that L would have to then be parallel to P? So we look back, that should look familiar to you. Theorem 3.12 talked about perpendiculars, but Theorem 3.11 said if we have two lines that are parallel to the same line, then they are parallel to each other. So really this one right here is going to be the reasoning for L being parallel to P. So we could say, explain why L is parallel to P. We would say L is parallel to P by Theorem 3.11. We could actually say that. Or we could say L is parallel to P because L is parallel to M, and M is parallel to N, and N is parallel to P. So L is parallel to P. Okay? Either way of stating that would be fine. Just remember, Theorem 3.11 will change from book to book and from course to course. If you're in Foundations of Geometry versus regular geometry, the theorem number may be different because regular geometry does more theorems and postulates than a Foundations of Geometry class. So just be careful about that. It's truly better if you can know what the theorem says versus what number the theorem is. Okay? All right, so here's another example of applying this. Find the value of x that makes line AB parallel to line CD. Okay, so as you can see right here, we have a right angle, and we want line AB to be parallel to line CD. So, if this is a right angle, what would 2x plus 2 have to be equal to in order for these two to be parallel? Okay. Well, if we go back to some of our postulates here, or theorems, Theorem 3.12 says that if you have two lines that are perpendicular to the same line, then the two lines are parallel. So we can use that. These would be two lines, A, B, and CD, perpendicular to line AC, then the two lines are parallel. Okay, so we'll say right here for like an explanation. Oops, I think I spelled explanation wrong. if line AB is perpendicular to line AC and line CD is perpendicular to line AC, then line AB is parallel to line CD. So 2x plus 2 would have to equal 90 degrees. Now we can solve for x. So all of this was really my thought process above, and now I can solve. But if it did say explain, this would be the way that you would explain right here. Okay. So we solve this. You should be subtracting 2 first. Keep working on those algebra skills. This is 2x equals 88. Divide next. So x equals 44. And it just said find the value of x. We don't have to plug that back in. Here's some checkpoints. So use the information in the diagram to explain why A is parallel to C. You should probably pause this and then see if you got it right. So what we can say is if A is parallel to B and B is parallel to C, then A is parallel to C. So that would be your reasoning. In number 3, find a value of x so that D is parallel to E. That's the theorem 3.12 that we had. This one up here for number 2 was theorem 3.11. Okay. So we actually need to find the value of x in number 3. So that would mean that we need E right here to be perpendicular to this transversal. So we would need a right angle. So we'll set it as 15x plus, oh, I'm sorry, that's a 5x. That's a parenthesis in front of it. So 5x plus 10 equals 90 degrees. And now solve. Subtract and divide. So 80 divided by 5 is going to be 16. Almost done. So this right here, this is just kind of a summary, ways to show that 2 lines are parallel. So last time we talked about converse angles being, or the corresponding angles converse. So right here, show that a pair of corresponding angles are congruent. If you can do that, you can show the lines are parallel. Alternate interior angles converse, we did last time. So here we would need to show that the alternate interior angles are congruent. Alternate exterior angles converse. The alternate exterior angles would have to be congruent. And then your same side interior angles converse. Your same side interior angles would have to be supplementary. Okay, that one's different than all of the others. That's why I have it in blue. And then there's one more. These are the 2 we did today. Theorem 3.11, so show that both lines are parallel. You can just do the 2 slash marks to a third line. If you forget what that means, write it underneath. And then theorem 3.12, in a plane, show that both lines are perpendicular, the upside down T. To the third line. Okay. All right, ladies and gentlemen, that concludes our notes for today on 3.6, showing lines are parallel. Okay, have a great day, and get started on your assignment, please.